In the earlier video lecture series, we had seen limits, continuity, and the prerequisites in order to define the derivatives, which are the main idea we are moving on to in these sections. So here we have the section 1.3, which is the derivative as a limit and the Leibniz notation. To start off, our basic claim is that the derivative is the limit of a difference quotient. This is a basic idea as we move along this section. So suppose if we have a function f of x, say we have a function, and suppose a function is the graph which you are seeing here. Okay, so earlier you had encountered the difference quotient when you had a point ordered pair x naught comma f of x naught and another point ordered pair x naught plus delta x comma f of x naught plus delta x. So here you can see the points here. Suppose the point which you are seeing with the cursor is the ordered pair x naught f of x naught, and the second point is the ordered pair x naught plus delta x comma f of x naught plus delta x. And you know what is delta x. Delta x will be the difference, the length of the length in between x naught and x naught plus delta x, as well as delta y is defined as the length or the distance between f of x naught and f of x naught plus delta x. That's how we defined delta y. And we called delta y by delta x the difference quotient. So here in the figure, you can identify that this distance will be delta x as well as this distance will be delta y, right? So if this angle is called theta, actually delta y by delta x is tan theta, which is nothing but the slope of the line which is joining the points which we talked about now. So from that we understood that the difference quotient which is delta y by delta x is nothing but the slope of that secant line. So when we are talking about the same function, and suppose if this delta x is made closer, as you can see in the figure, it is made lesser and lesser here. So that means this line, the line which is joining the two points, will become closer and closer. Like when this is coming closer, right? Like this, and this is also coming closer, closer. These two lines are coming closer, closer together. That means this point will also become tending to this point, right? So that means there is an observation which we get there, which is that when delta x is small, the delta y by delta x will be the slope of the tangent line itself. That is, it is nothing but the derivative f dash of x naught. So also we know that if f of x is the distance as a function of time, then delta y by delta x will become the average velocity, and such ideas you can infer from that. So here the main observation we are getting from this is that f dash of x naught which is the tending value of delta y by delta x as delta x approaches 0, is nothing but the slope of the tangent line. And as we said earlier, if f of x is representing a distance function and with respect to the unit time, then f dash of x naught will be the instantaneous velocity at the time x naught. And here you can see the difference quotient definition, which we had already dealt with. Okay, so we are formally defining the derivative. Suppose we have a function be it f of x and its domain is an open interval which contains x naught. We say that f is differentiable at x naught if limit delta x tends to 0, f of x naught plus delta x minus f of x naught divided by delta x, and that is denoted by f dash of x naught, and it is called the derivative of f of x at x naught. So this is nothing but limit delta x tends to 0 delta y by delta x, the same thing. Okay, so as we said, suppose if we have a function. Okay, so you have a function something like this. Okay, and we are thinking about the derivative at x naught. What did we say? Correspondingly, we know the function will be f of x naught. So if here you have some x naught plus delta x, so the corresponding value of the function will be f of x naught plus delta x, and you were talking about this line which joins these 2 points. Okay, as this is moving closer and closer towards x naught, as delta x is tending to 0, you know that x naught plus delta x is tending to x naught. So what happens is that this line which we have drawn moves closer and closer, and that will reach this point itself, and then we can say that what we are calculating is nothing but the slope. That's what we just said now in order to repeat for the same. So we'll just see example 1. Example 1 says that suppose if f of x is equal to x square, then f dash of 3 is equal to 6 by the quadratic function rule, with a is equal to 1, b is equal to 0, c is equal to 0, and x naught is equal to 3. Justify that f dash of 3 is equal to 6 directly from the formal definition of the derivative and the rules of the limits. This is something which we had proved earlier, and we have to prove the same with respect to the formal definition. So the difference quotient is written delta y by delta x is equal to f of x naught plus delta x minus f of x naught divided by delta x, that is equal to, we have f of x is equal to x square, right? So when it is 3 plus delta x, you have 3 plus delta x whole square minus 3 square divided by delta x, that is equal to 6 into delta x. You just solve it. You get 3 square plus 6 into delta x square minus 3 square. You cancel out 3 square and 3 square. You get 6 delta x plus delta x whole square divided by delta x. Now you can simplify this fraction, since delta x can be cancelled out as delta x is not equal to 0. And by the replacement rule of the limits which we had discussed earlier in the earlier sections, you have limit delta x tends to 0, 6 delta x plus delta x the whole square divided by delta x. You cancel out the delta x from that. How? This is equal to delta x into 6 plus delta x divided by delta x. Okay, so you are left with 6 plus delta x there, right? So limit delta x tends to 0, 6 delta x plus delta x whole square divided by delta x is equal to limit delta x tends to 0, 6 plus delta x. And both of them are same by the replacement rule. So here 6 plus delta x is a polynomial, and when delta x is tending to 0, you know that 6 plus delta x will tend to 6. So that's the value we get at f dash of 3. So that is 6, which is verified. Now example 2. Use the formal definition of the derivative and rules for limits to differentiate x cube. Okay, so here you have f of x is equal to x cube. We are not given a particular point, so we assume that that point is x naught. Okay, so we have f dash of x naught is equal to limit delta x tends to 0, f of x naught plus delta x minus f of x naught divided by delta x, that is equal to limit delta x tends to 0, x naught plus delta x the whole cube minus x naught cube divided by delta x. You know that a plus b the whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Using that, you expand minus x naught cube, cancel them out, and then cancel out the commons. How? Here you get limit delta x tends to 0, delta x into 3x naught square plus 3x naught into delta x plus delta x the whole square, the whole divided by delta x. So you can cancel them out to get this by the replacement rule. So you get when delta x is tending to 0, you have this term tending to 0 and this term tending to 0, you get that is equal to 3x naught square. So what you get is the derivative of x cube at x naught is therefore 3x naught square, or we can say that f dash of x naught here is equal to 3x naught square when f of x is equal to x cube. So this is what we got in this example. Now example 3 asks us to find f dash of x for x not equal to 0 when f of x is equal to 1 by x. So first you have to find the difference quotient. Delta y by delta x is equal to, you have f of x is equal to 1 by x. So instead of that you have, okay, so you have delta y by delta x, that is equal to f of x plus delta x minus f of x divided by delta x. Okay, so that is equal to 1 by x plus delta x minus 1 by x divided by delta x equal to, you simplify the fraction. Okay, so you and use the LCM. So you get, if you have any doubt, so there you have 1 by x plus delta x minus 1 by x the whole divided by delta x, that is equal to 1 by x. You take the LCM of the fractions there. So you get x minus x into 1 minus x plus delta x divided by x into x plus delta x, the whole divided by delta x. Okay, so from that you get delta x by x into x plus delta x into delta x. And here x is being a constant because we are tending delta x tends to 0. Okay, so now you are taking delta x not equal to 0, limit delta x tends to 0, delta y by delta x is equal to limit delta x tends to 0 minus, here you can cancel them out, right, since delta x is not 0, minus 1 by x into x plus delta x. And when delta x tends to 0, we had talked about the continuity of rational functions earlier when you had the fraction of polynomial functions coming like this. When delta x tends to 0, you get, you just substitute instead of delta x 0, so you get minus 1 by x square. So what you obtained is f dash of x is equal to minus 1 by x square. So in all these examples, we saw that when f of x is equal to x square, you got f dash of x naught is equal to 2 x naught, 2 x naught. When f of x is equal to x cube, we obtained f dash of x naught is equal to 3 x naught square, and so on. So here you can have a general form which you already know, that if f of x is equal to x raised to n, where n is a natural number, you can say that the derivative of f at x naught is equal to n into x raised to n minus 1. So that is a general observation you can make from there. Now the next question is about differentiating the root of x when x is strictly greater than 0. The difference quotient is delta y by delta x is equal to, what do you have here? Yes, you have delta y by delta x to be calculated, that is equal to f of x plus delta x minus f of x divided by delta x. So f of x plus delta x is equal to root of x plus delta x minus root x divided by delta x. So in order to cancel delta x from that, what do? We rationalize the denominator by multiplying both of the numerator and denominator by root x plus delta x plus root x. Why? Because we have to rationalize, we have to rationalize this guy sitting here, the numerator. So you have to multiply it with a term having the plus sign here. So you get delta y by delta x is equal to, multiply the term with the plus sign here, and you get, when you multiply you get x plus, this is of the form a minus b into a plus b, so you get a square minus b square, so you get x plus delta x minus x divided by delta x into root of x plus root x plus root x, and in the numerator these guys cancel out, then you have a delta x that also cancel out there, so you, what remains is this. Now you have to apply limit delta x tends to 0, delta y by delta x, so that is equal to limit delta x tends to 0, 1 by this term sitting here. So you know from the earlier section that limit x tends to x naught, root x is equal to root x naught. So here you can substitute instead of delta x, you have a 0 there. So you will get Here it doesn't have any delta x, so you get 1 divided by root x plus root x, that is nothing but 1 divided by 2 root x. So what did you obtain here? When f of x is equal to 1 by x, we have f dash of x naught is equal to 1 by 2 root x naught. This is the observation we make from here. And this is a very important theorem which is coming along, which is suppose a function is differentiable at a point, then the function will be continuous at that point. So the statement is if f dash of x naught exists, then f is continuous at x naught, that is limit x tends to x naught, f of x is equal to f of x naught. So the main thing we have to remember is that limit x tends to x naught, f of x is equal to f of x naught is same as limit x tends to x naught, f of x minus f of x naught is equal to 0. Okay, so we have to prove, what do you have to prove? This is the thing we have to prove. Okay, so and the equation sitting here and the equation sitting here are the same. So we have to prove this because both of them are same. The statements are same. Okay, so you know that delta x is equal to x minus x naught, assuming delta y is equal to f of x naught plus delta x minus f of x naught. Okay, then you're considering limit, you can call it limit delta x tends to 0 delta y is nothing but limit f of x minus f of x naught plus delta x minus f of x naught the whole there is no enough the whole divided by delta x tends to 0. This is what is meant by limit delta x tends to 0 delta y, we know that. So the same term is taken, limit delta x tends to 0 delta y, that is equal to, we can divide it by delta x and multiply it with a delta x, that is one and the same. Okay, and by the property of limits, the product rule, you can split the first term and write it as a product. So that is equal to limit delta x tends to 0 delta y by delta x into limit delta x tends to 0 delta y. And we have defined this to be f dash of x naught. Okay. So this is f dash of x naught, and you know that limit delta x tends to 0, delta x is equal to 0. So you get limit delta x tends to 0, delta y is equal to 0. So what did we obtain now? We obtained this. So we have proved our claim. And so what we obtained here is differentiable at a point implies continuous at that point. Okay, so the next thing is that continuous at a point, next example is continuous at a point does not imply differentiable at that point. So that is the next example. So we are given the function f of x is equal to mod x. Mod x. What is mod x? Mod x is equal to set x when x is greater than or equal to 0 minus x when x is strictly less than 0. That is mod x. Okay. We are going to say that it has no derivative at x naught is equal to 0, but it is continuous at x naught is equal to 0. So that means here we have the function f of x is equal to mod x is continuous at x naught is equal to 0, but it is not differentiable at x naught is equal to 0. That is what we are going to see. So this is the function f of x is equal to mod x. You can see it here. So for that, the difference quotient is taken at x naught is equal to 0. That is delta y by delta x. That is equal to f of x naught plus delta x minus f of x naught by delta x, and where it is taken at x naught is equal to 0. So that means that is equal to f of 0 plus delta x, that means delta x minus f of 0 divided by 0 plus delta x, that will be delta x. And our function is mod x, so that you get mod of delta x minus f of 0 mod 0 is equal to 0 divided by delta x. So you get mod of delta x by delta x. So that is what you obtain here. Okay. And what is mod of delta x by delta x? That will be, yes, you can split into two parts. One, when delta x is strictly greater than 0, and minus 1 when delta x is strictly less than 0. How? Because to make it more specific, that will be when delta x is greater than or equal to 0, that will be delta x by delta x. When delta x is strictly less than 0, that will be minus delta x by delta x. So you get 1 when delta x greater than or equal to 0 minus 1 when delta x is strictly less than 0. So that's how we obtain that. So the function is like this, and we cannot have the limit this. So it doesn't exist, does not exist, because we cannot move it to a certain value. So the derivative does not exist there. So that's what the example says. And also note that as x tends to 0, x is coming from the left, x is coming from the right, you get the function is moving towards 0, and the function will move towards 0. That's how we can see from the figure. So this proves our claim. Now, what is Leibniz notation is that a function y is equal to f of x. The derivative can be written as dy by dx and df of x by dx, d by dx of f of x, d of f of x by dx, and so on. And also sometimes it is written as at x naught, it is written as dy by dx at x naught, df of x by dx at x naught, and so on. Um, these representations are called the Leibniz notation. It is not a big deal. You are already familiar with that. So keep in mind how it is given the name, the Leibniz notation. And the The next example, so you can work out, you have to find if the function is 3x squared plus 2x, then you have to find the derivative. You know what the derivative is, find it. That will be 6x plus 2. And similarly, you can find and solve example 6 to find the slope m of the graph y is equal to root x at x is equal to 4. You know it is a derivative, so derivative will be 1 by 2 root x of root x, and substitute it at 4, and then find the velocity v of a bus whose distance is t cube. So you get d by dt of t cube is equal to 3t square, and likewise you can find the derivatives. You are already familiar with finding derivatives, that is what we know. And also you can read the supplement to the section for if you are more interested in a real life example about filling a pond. After the section, you can solve and find derivatives of the questions we are going to mention: 2, 9, 12, 20, 24, 25, and close this section. So thank you for watching. See you in the next video lecture.